thing I'll focus on today will be for support of the HydroAir wave energy turbine that is currently mounted and on its way to Hawaii on the Ocean Energy 35-meter buoy. I'll start with just an introduction of myself, give you a little bit of my background, both education and work history-wise, and then we'll go into a little bit of the fundamentals of an oscillating water column. Maybe that's old news to most of you in the room, but perhaps it's not for everybody. Then we'll talk about the HydroAir turbine and what it is, the operating principle behind that. Also talk about a test facility we recently commissioned in Redmond, Washington, here nearby. That's where that picture on the left was taken. And then we'll talk about, again, the buoy headed to Hawaii, which is at the 500 kilowatt system. So first off, a little bit of my background. I actually started at Washington State, got a mechanical engineering degree, minor in material science, and graduated in 1995. My wife got a job and forced me to cross over, and at least for my graduate work, attend here at the University of Washington. If you ask who I root for in Apple Cup, refer to line 1. As Paul mentioned, I did some work for Dr. Tuttle at that time. It was actually a Boeing-sponsored project, so this was a pre-787 fuselage, and so we were looking at carbon fiber composites and long-term durability. So I had over a year-long project where we put composites under load and then in an oven at temperature to kind of do accelerated life testing and then check mechanical properties kind of along the way. And that's how I stepped into my first full-time job, which was at Boeing in '96. As an undergraduate at WSU, I did have a couple internships with Pacific Gas and Electric, specifically with Morro Bay Power Plant, which is a natural gas-fired plant on the coast of California. But again, for the first full-time gig, it was with Boeing in their materials and process division in Renton. I kind of took a gamble, and a guy I went to grad school with here at the U just started at a small company called Adroit Systems, and so after a relatively short time at Boeing, I jumped ship, and I was employee number 16 at ASI. So there's a common theme here as I go from companies with 10 or 20 employees to companies with 100,000 or 380,000, which is how many coworkers I currently have at Siemens globally. So that was a great experience, small company. We did lots of interesting work on pulse detonation, and spent time at China Lake Naval Weapons Center and Edwards Air Force Base, and then ultimately we got acquired by Pratt & Whitney. We formed a little Seattle Aerosciences Center kind of skunk works team, did that for a number of years, and then I jumped back to a small company called Ramgen. I don't know, maybe I was employee 18 or so for Ramgen. There we were doing supersonic compression technology. We had a Department of Energy contract. We teamed with Dresser-Rand, who ultimately acquired us in 2014. And then 1 year later to the date, Siemens bought Dresser-Rand. So I went from 20 coworkers to 7,000 to 380,000 in 12 months. And that's where I'm at now. And in May it was announced they're going to spin out all of the energy part of Siemens into a new company called Siemens Energy. Logo to be determined. So at any rate, as you look forward to your career in industry, I've only actually applied for a job twice in my life, but these are all the places I've worked. So it's interesting to see how it plays out. But I've got to do a lot of interesting different things. I actually gave a similar talk here at the U in 2009 in the ME department, but I guess I was only up to about here at that point. Okay, so again, maybe this is old news for the audience here, but why wave energy? In terms of an untapped renewable resource, there's certainly the potential for a significant amount of electric power generation, and you can read the numbers up there, but we could be looking at providing up to 1/4 of US power from that source. That's a great story from a potential perspective, but as we all know, anything on the ocean is hard, and actually converting that potential into reality is a challenge. You know, in my role, and I meant to include a slide on this, but our team here that I lead in Seattle, well, it's actually our office in Bellevue, and then the test facilities in Redmond. I've got 15 people under me here. And again, we're, for lack of a better term, we're kind of a skunk works operation. We're involved in this. We're also involved in compressed air energy storage, pumped heat energy storage, gas turbines, supercritical CO2, waste heat recovery cycles, just driving cost out of standard centrifugal compressors, which is kind of the bread and butter product line for oil and gas applications. So we touch on a lot of different things. This is just one project that we're working on and supporting. We have team members in New York, we have team members in Norway, France, Germany, India, and Texas. So I'm usually on the phone at 6 a.m. every morning because we're the last ones out of bed in the world. But it's an interesting place to work where we get to touch on a lot of different things. So the two things to note on the map there, again, maybe old news to you guys, is the WETS Wave Energy Test Center, which is a Navy wave energy test site currently in operation off Oahu, and then PacWave, which is a DOE-funded site that, well, it's not NEMREC anymore. Is it PMEC now?
PMEC, yeah.
That obviously PMEC is heavily involved in bringing that to reality. And ultimately, we'd like to take that 35-meter buoy to a different higher energy wave site, and PacWave would be high on the list of where we might go next with it. Okay, so an oscillating water column concept. I think this is the simplest graphic I've found that kind of demonstrates, you know, what we're talking about here, and it's you know, any chamber you create over the surface of the water, and then as the waves go by, water level in the chamber goes up and down. That can force air in and out of a hole, and if you put a turbine of some kind on that hole, you can make power. Now, the beauty of this, well, there's a few really nice things about this. One, you know, let's get all that electrical and moving part stuff out of the water, which is big. This can be deployed onshore in like a shore break type embodiment, or it can be offshore on a buoy, like the one that's headed to Hawaii. And there's a few different companies out there, Ocean Energy being one of them, that have, you know, some technology around how to make a more effective OWC, you know, i.e. deliver the most possible volumetric airflow and highest pressures in response to certain waves. We're currently teamed with OE, obviously, but you know, we're the turbine generator supplier. So you know, we're OWC agnostic. You know, if somebody's got a better mousetrap on the OWC side, we can put our turbine on it, so to speak. So the trick on a turbine, you mount like that, is it's got to be bidirectional, right? So the air goes one way for a few seconds, and then the air goes the other way for a few seconds. Now, historically, what's I don't have a graphic for it, but something known as a Wells turbine is what is kind of typically used. A Wells turbine uses a very different kind of airfoil design compared to what we use, and it's also fairly inefficient because you have this kind of massive variation in flow and direction and angle on the blades. There's just parts of the cycle where you're gonna get flow separation across your airfoil every single cycle at some point in that cycle. We overcome that by using an impulse turbine. So our rotating bit is down here at the bottom, right? And laser pointer worked this morning. I guess it'll still work like this. So these are the impulse blades right here. There's the rotor shaft, generator. So all this structure out here is all just fixed components. Now, these guide vanes are the key, and that's really the fundamental to the HydroAir concept. Is those guide vanes will turn the flow and put some swirl in the flow. Now, due to conservation of angular momentum, as it comes down in radius, it swirls up even more. And these impulse blades are basically shaped like a U in cross section if you look radially down into the blade, right? So if I've got flow that's coming in with swirl, it'll spin the blade, right? And conversely, on the other side, if I got guide vanes over here that swirl the flow, it spins in the same direction. So that's the key. You can't be reversing the direction of your rotor every single cycle. So by moving the guide vanes out to a very large radius, we can turn them just a little bit, and then with the conservation of angular momentum, that flow swirls up even more by the time it gets to the vane, to the impulse blade. Okay, so when you go backwards across that, the flow deswirls, and so when you encounter a guide vane that's kind of going the wrong way, right? You know, I want to turn flow this way when it's sucking in. When it's blowing out, it's actually a loss device. You don't actually want it there. Now, some people have tried to address that by having movable vanes on each side. You know, and they're constantly doing this with every single cycle. But you know, once you get into movable geometry and trying to make the last and not foul up and the barnacles grow on it, it stops working and all these kind of issues, right? So, you know, the beauty of this is nothing's moving except that spinning rotor. And so by moving those guide vanes out, and you know, we sometimes refer to as a variable radius turbine, we basically can run flow both directions and pay the least penalty when we're going backwards across the guide vanes. So that's, you know, that's the basic concept. It's good in that it's simple, and then you get into the complexity of trying to make it real, and that's when things get hard. So we've got a lot of composite materials in this thing you know, obviously for the marine environment that can have a lot of benefits. If these things are going to be offshore, we obviously want them to be very low maintenance, you know, things like that. And we can install this thing vertically or horizontally, you know, just kind of depending on what kind of a OWC chamber you're hooking up to. Okay, so another part of all this work, and this is really how when I first met Brian Pelagi and got a little bit more involved with what was at that time NEMREC. The state of Washington Department of Commerce has a clean energy fund that the governor established, I guess about 4 years ago now. In the third round of that funding, CEF3, we submitted a proposal where, you know, we would bring in, you know, roughly 50-50 cost share and build a test facility in a pre-existing lab we had in Redmond where we do turbo machinery testing. So the point of the facility, right, is to be able to obviously be able to repeat conditions, which is pretty key because you don't really get to pick which waves are coming, right? So when I change something on my turbine, well, is it better or worse? Well, I don't know. The waves were different that day, right? So what we're able to do with this thing is the blue and green box is exactly that. It's just a great big box. There's an air piston, and I'll show you pictures here in a moment, that we move with a hydraulic cylinder back and forth, and that just simulates the water level going up and down. It just happens to be horizontal in this case, but the water level going up and down in an oscillating water column chamber. And then on the end wall, and you can see at least a conceptual design of a turbine, you know, mounted on that end wall, and then we can change things about the turbine design. We could play with the inertia. On the electrical side, power smoothing and storage is, you know, because that's one thing, right? The power produced by this thing is constantly going up and down every way, right? We actually keep the rotor speed pretty constant, but sometimes it's being pushed hard and we're drawing lots of power out. Sometimes we turn the generator way down, right, so that we don't slow the rotor down between waves. So it's a very dynamic system, and it puts dynamic requirements into your electrical side, which drives costs. So there are things like that in terms of, you know, power smoothing and new geometries. The one we've built is a quarter scale size of the one headed to Hawaii. So if we encounter issues out in the field, we can maybe kind of simulate those and, you know, try try different ideas in the lab environment. Obviously a little easier than trying to go offshore and deal with something like that. And we kind of envision this just kind of supporting the development of this product line in terms of trying to drive cost out, levelize cost of electricity, right, being your key metric when you're competing against other ways to generate electricity. And then also, as we identify customers, as an example, there's a harbor in Italy that has a shore break around it with OWC chambers, right? And they can measure basically the time versus pressure history in the chamber. We could take that, simulate it in our lab, hook up a turbine, and then when we deliver a turbine, we could say, oh, well, we're going to guarantee this much power for this kind of wave input, and so all the contractual things that come up with actually selling turbo machinery, we can help address with the facility. Now, we're only going to get, well, and we did, as you'll see, we just actually commissioned this facility, around 50 kilowatts of power out of this. One thing about turbo machinery is it's very non-linear in its scaling. So it's a 1/4 size, physical size turbine doesn't give you 1/4 of 500 kilowatts. Turbo machinery scales tremendously, which is why you can get an airplane like a 777 even off the ground. All right, so here is some pictures of that test facility. We just commissioned it in September. We can actually generate around 350 kilowatts of pneumatic power. So depending on what turbine we hook up, we can run some pretty big stuff. So for shore-based applications, fundamentally a lot of the wave energy is dissipated by the time it gets to shore. So you might have a product that's a 25 kilowatt turbine for a shore-based application. Offshore, you want to be talking 500 kilowatts, megawatt, real utility scale kind of numbers. So we can kind of subscale the offshore stuff, but we can do full scale testing of those shore-based turbines. So in the picture in the upper right, that's an 11.5 foot by 11.5 foot aluminum wall, basically. We push that thing back and forth with a 30,000 pound hydraulic ram. We've got an 800 horsepower motor driving a hydraulic pump to drive that thing. And when it moves back and forth, it's pretty impressive how much air you're moving around. So kind of on the opposite wall to the air piston, here's the end wall. This is where we've got a turbine, a HydroAir turbine mounted up. So you can see the ducting. The guide vanes are out at this diameter where you see all the small bolts come through. And then obviously there'll be the rotor shaft, bearing housing, and the generator. Yeah.
So I don't know if I missed this, but you don't actually have water in there. You're just simulating.
Correct.
Basically, that piston takes the place of the top of the water. Exactly.
So water being an incompressible fluid, I can treat it like a metal wall moving back and forth, right? And even if there's some chop on the surface of the water, the reality is it's all just about how much displacement you're getting, right? So there's been other more, I'll say, benchtop scale facilities like this built in the world. As far as we know, this is the biggest one anybody's ever done in terms of power capability. Okay. So the 500 kilowatt. So this is the one that was just built down in Portland and is being towed out to Hawaii as we speak. So this was actually the Ocean Energy 12-meter buoy with their own kind of in-house. Well, that's actually a Wells turbine type design. So the Wells turbine it uses a different blade design. It doesn't have that radius change to get your efficiency up. So Wells turbines are very efficient in a very narrow window of operation. Our window of operation is significantly more broad, which all just translates into a higher annual average output of electricity, right? So that testing was, I think, 9-10 years ago now. Things take a while in industry, but this is their model of the 35-meter buoy, and this is the model of our turbine mounted to it. And there's the real thing. So this was built at a shipyard down in Portland, Vigor. Is the name of the company, the shipyard there. You can see obviously our turbine mounted on the top. You can also see the kind of iceberg effect of how much of this thing actually is under the water. It's an interesting concept that OE has to kind of amplify the magnitude of the pressure you develop. So the OWC chamber, right, is kind of everything above the black line, right? So all up in here, that's all air all the time. That's your captured volume of air. So as the water level's going up and down here, you're driving air in and out of the turbine right there through this chamber. They call this a reverse bent duct design. So it's actually mounted so that the waves come this way. So you'd be anchored to the seafloor from a couple of points here. So this is the bow on the side facing away from us, for lack of a better term, that's facing into the waves. The operating principle here is that as this entire thing, and you actually size it kind of as a function of the wave period at the site where you're going to deploy. You want this thing to actually be riding up a wave and then riding down a wave. Now what happens is there anybody standing? Yeah, there's a guy for scale, right? So I don't know, what are these, 25 feet tall chambers, and this thing's about 30 feet. No, that doesn't make sense. But 75 feet wide. Yeah, if each of those, maybe it's 20 by 60, but each of those three chambers, they're full of water all the way to the back. Now, as this thing rides up a wave, you've got, think of how many tons of water are in there, and it all wants to run downhill. Either towards the chamber or away from the chamber, depending on what downhill is, right? And it's that kind of hydraulic amplifying effect that is basically the premise of their whole design. So, as opposed to just making a simple chamber that, why does it have this long leg part, right? Well, that's the reason why. You could just make a chamber that was just that, and yeah, the water level goes up and down, but you're just not going to get the volumetric flow out of the machine that you could with this approach. Yeah.
So the whole assembly rocks like this motion when
Yep.
it's in the water?
Yep. Yeah, as you kind of picture a wave, and these are offshore waves, right? These are big waves, fairly long periods, so a buoy of this length is kind of the right size. But you can kind of picture a wave hitting this end of the buoy and lifting that end. Well, this end is down in a trough, right? Between two waves, and then vice versa. And so that gives you this kind of effect that you'll see.
Question.
Yeah.
Do you know how that compares to if you were just using like the top surface of the wave, like in terms of like power, like airflow?
I don't have those numbers off the top of my head, and I go ask my partners at OE, right? That question. It's a good one, and then probably something I should know off the top of my head. But in terms of how much benefit are you getting, right? That is something that I'm sure they've quantified, but I don't have handy off the top of my head. So if you ever build a 900-ton, 35-meter long buoy and you want to move it to Hawaii, it's just kind of a fun website to go look at. I recently became familiar with. First, you hire a 100-foot-long tugboat, and then it travels at 2.2 knots. So it's getting there. This screenshot was from a while ago. I hope the little blue boat is closer to Hawaii if he's going to make it by November 30th, which is what they're projecting the arrival is. I actually kind of wondered what does crew duty look like on that tugboat. 2.2 knots for a month or so, 24 hours a day. Lots of poker games, I think. That's what it looks like. But it is an amazing website to go to if you've never gone, because pretty much every ship and boat in the world that is at least communicating with satellites you can see on there. There's similar aviation type maps you can go to and see 8,000 airplanes that are in the sky at any moment. It's the same kind of thing on all the shipping lanes. It's pretty amazing. All right, so that's in terms of prepared slides. It was, you know, everything I had. There's just I took that shot, I don't know, a month ago down in Portland of the unit on the buoy. So that, just for scale, well, obviously there's a person there, but you know, the duct is about 7-8 meters in diameter, and so we're a little under 2 meters in diameter for the one in our lab for that quarter scale. Questions?
What was the most challenging part about figuring out how to make the test facility? What problems did you run into, if any? If it was pretty straightforward, I mean, that's also.
Well, you know, we kind of follow a standard design review process, as we refer to it, right? And we start with setting requirements. What do we want this thing to do, right? We want to make X amount of pneumatic power. Once we do that, so conceptual design phase, okay, well, let's brainstorm. What could we do to design something to meet those requirements? And then the preliminary design, a final design, drawing release, you know, in the, you know, setting the requirements is reasonably straightforward. We knew, you know, there's some uncertainty there. Well, just how big are we going to be able to go and all that, but we knew we wanted a meaningful scale. And in the conceptual phase, kind of to the water question, right? We even thought, should we pump water around between two tanks, right? Do we do that and just have big pumps, one going one way and one going another, just move the water back and forth? Or, you know, there was I don't see any chalk, but there was a rotary idea, right? Let's have a big cylindrical drum with a rotary flapper valve in it and kind of a tangential takeoff of the air. So you swing the door this way and swing the door that way. So those are all the different kind of concepts we looked at. In terms of, you know, you got to look at, well, how much is it going to cost, and how much, what's going to perform, and how is it going to perform, I should say. And, you know, when we settled on that design as kind of the best compromise of all those, and really for the, you know, we had a 20-foot wide by 60-foot deep test bay, and so there's that physical constraint. Right? What's the most air we can move around? We already had an 800 horsepower electric motor, so we're like, okay, well, that kind of sets the limit on one, what can we drive an electric motor, and well, that ended up setting limits on the hydraulic system, and so all those factors played in. Originally, when we kind of settled on this concept, we're like, well, of course, this chamber is going to be round, right? Because it's a pressure vessel. Well, okay, that you knock off a lot of interior volume. So in terms of the volumetric flow rate you're moving, just cut that way down. Building a round vessel, as opposed to buying I-beams and pieces of sheet steel, right? It's a lot more expensive. And so ultimately we looked at it and said, well, okay, it's not structurally efficient, but it's a lot cheaper to throw bigger I-beams at it than to go get custom rolled, formed sheet and reinforcement. The walls of the thing move, you can see it. But you know, we had our FEA models that were pretty close. Some of the deflections were a little bigger than we maybe anticipated, but nothing welding on a couple more steel struts didn't fix. Yeah.
Do you know what kind of peak pneumatic pressures you're getting inside your test chamber?
Yeah, the maximum pressure that it's designed to is 1.6 psi. So just the pressures these things generate are not very high. But think about that. So, you know, you're 14.7 ambient, and we're only going up to 16.3 is kind of the maximum design. And even at 1 psi, you can watch the walls of this thing move around because it's just a huge area. So it's a fundamentally, these are low pressure, high flow devices. And so you got to design your turbine for that, right? We're not talking about a turbine in a gas turbine engine where you're crazy high pressures and temperatures and all that.
How loud is it?
That depends. It's actually pretty quiet. And that's definitely absolutely something we've kept in mind in the design of this thing. One thing that really works in our favor is that the turbine rotor is really kind of buried down in the flow path, right? It's not like you're looking right into the inlet of a gas turbine engine hanging from the wing of an airplane, right? It's buried down in there. The speeds are very low relative to, ideal with turbo machinery spinning at 30,000 RPM. Some of our other products we work on, this is hundreds of RPM. So it's low speed turbo machinery. It kind of goes along with the low pressure, high flow. And so you can stand where that picture's taken while it's running, without hearing connection, right? The hydraulic pump is probably louder in the back, right? Driving this thing.
I'm curious what the air coming out of it is like. It seems like you have a lot of flow in a pretty small area on the exit of the turbine.
Right. So all the flow going in and out of the system is through that annulus right there, right? Because the other annulus is just a mirror image, is obviously attached to the chamber. Again, if you stand about that far where the picture's taken, but go right in line with it, you'll feel a breeze in your face, but it's not going to knock you over or anything. It dissipates quite a bit, obviously, as you go out of an annulus this big and jets into the room. But yeah, not too bad. Interestingly enough, the design of the facility, think about that big air piston inside this chamber coming at you, right? And pushing all this air out right here. Well, where does that air need to go? That's right. It needs to go back down the hallway on each side and then fill in the back behind. And so stand in the hallway and it's like, we're like, oh, it's going to be like a 45-mile-an-hour wind. Add kind of, turn this thing to 10 and run it at max capacity, right? And so we had to think about, are we going to knock the insulation off the ceiling and those kind of practical things that come up. Yeah.
So there's no water here, but
Right.
in terms of salinity
Mm-hmm.
and how that affects the turbine, do you take that into account, or how much do you think that affects?
Well, we do. I mean, the primary thing where we take it into account is corrosion, right? So in terms of the materials selection, so in this particular case, in both of these, the ducts are composite materials, fiberglass, epoxy composites. Those ducts were actually built by a boat builder in Anacortes, Betts Marine. Kind of a fun shop to walk through. They have lots of rich clients and custom boats. So they kind of saw this as kind of a fun side project. The turbine on the right was actually built in England. Part of our team, and really, the whole HydroAir products was in existence before I ever became part of Siemens. And so part of our team is in the UK. Those were built over there. The blades on the one going to Hawaii are actually carbon fiber, the actual rotating blades are carbon fiber. We did aluminum blades over here. Both those materials are, pretty good in a marine environment. We used aluminum pretty much just as a cost savings. We were more interested in exploring their aerodynamic performance. So whether your blades, aluminum, steel, carbon fiber, aerodynamically, it's kind of perform the same, but in terms of putting a product out in the ocean, that's primarily what you're going to have to be concerned with. For the rotor shaft and those kind of things, it's pretty much all stainless steels to deal with that. Yeah.
What kind of torques and RPMs are you getting out of the rotor at the lap scale and at your scale?
So the full scale unit is going to run in the 300 to 700 RPM range. Again, because of the nature of how you scale turbo machinery, to get the same aerodynamics on a smaller turbine, you got to spin it faster. So we've spun this thing up over 2,000 RPM. Was it torque was your other question? I don't have a good torque number off the top of my head. You pretty much, and we're not, there are, you can put strain gauges on shafts and torque meters, those kind of things to measure that directly. We just kind of infer it from our speed and our power, right? So this whole thing, we've got what's called a variable frequency drive. It's really just a whole bunch of electronics that can power a variable speed motor. That same VFD that's running the 800 horsepower motor to drive the hydraulic pump is taking the power being generated by this generator. So we might have 400 kilowatts going into driving the hydraulics, and we're only making 40 back here. So we'll just feed that right back into the VFD, and it just kind of translates into us pulling less power off the grid to run the facility. But that's how we look at the powers being generated. Yeah, it's much better to let the ocean move your piston back and forth. It's a losing proposition to drive it yourself.
For that full scale one, has it been tested in any way, or is it essentially just because this small scale worked, we'll assume that the design will hold that full scale?
That is a great question, and that gets into the nature of when you get into industry, things don't always go in the order you want. Because there's lots of other things at play, funding and how much risk you're willing to take. So that was started way before we did any of this. When we saw this opportunity, our target was to get it commissioned this fall so that we have this thing run before that one, which took many years to build, was ready to go. So the good news is we've learned some things running this one that we're definitely incorporating into that. Not so much in the well, which should have been 9 meters instead of 8 meters, but more in the control strategy. The control of these things is really, really interesting. Again, because it's so variable. That's why you need on the electronic side, every single cycle, you're varying how much load you're putting on that turbine so that it holds speed. So we've tried different control strategies in the lab, definitely found some characteristics that we like better on one versus the other. And so we're rolling those kind of lessons, into that. And ideally that's the order you do it in. But I think your fundamental question is no, that's never been run before, right? There's no test facility big enough to do it. There's things, the rotor was spun and we made sure it was balanced and those kind of checkout things you can do. But as a system, never been run before. And at some point, you just kind of have to take a leap, right? So we're taking a leap. Yeah.
Does Siemens think that you'll use this turbine in other applications like a compressed air system, or is this oscillating water column?
Yeah, I mean, if you talk about when you say this turbine, if you're just kind of referring to the design, right? It's very tailored to this kind of an application. There's really not a lot of other applications where you see low pressures, high volumetric flows, right? It's kind of unique to that. Now, a lot of the air turbo machinery and aerodynamic design principles apply equally well. It's just you just end up with a very different looking machine.
You can't really spin this in reverse to compress anything. Like, what would that look like? What would the airflow look like if you spun the blades in the opposite direction?
Well, it would just churn because these are completely symmetric blades, right? A compressor blade has an inlet and an outlet in a specific airfoil shape, right? Flow is going to go, even just by spinning it, it will ingest flow and do its compression work or add energy to the flow. These are completely symmetric, so it's just going to kind of churn. Don't do anything. Yeah.
So thinking about maintenance of OWC things, can you safely go inside an oscillating water column, or will the pressure mess you up?
The latter. Any scuba divers in the room? Yeah, they were clearing your ears. I think if you stay ahead of it every few seconds, the pressure on your ears is changing. It's not that, 32 feet or whatever, it is, 1 atmosphere, so you're at, 28 psi. And we're only going up 1 psi. So it'd be like sticking, maybe it wouldn't be that bad. Don't be sticking your head in the water like 3 feet deep and back to the surface every few seconds. But in general, no, you wouldn't go in there. And really, there's nothing in there. It's just a big box. So from a maintenance perspective, you shouldn't need to. One thing we have on this rig, which the test facility doesn't, you can kind of see right here these little boxes sticking out radially. Those are actually each a pneumatic actuator, and they each control an annular segment of a blocking valve. So for maintenance of the turbine, we can say, okay, all you guys close, and we can isolate the turbine from the chamber, right? And so if I needed to go replace the generator or pull the rotor shaft or whatever, we've got that capability. We've also got that as kind of a fail-safe in a storm condition. If the thing is just putting out way more pneumatic power than we should be trying to handle, we can just shut it off.
Like wind turbines have to.
Yeah, sometimes they'll feather their blades, right? And we're not going to make any power. It's in the 100-mile-an-hour storm wind, right? So it's the same kind of philosophy from both a maintenance and a safety perspective. Yeah.
Well, can you talk about the state of like the compressed air storage that you were talking about?
Sure. So Dresser Rand, who was on one of my first slides there and was acquired by Siemens in 2014, the only utility scale operating compressed air storage system in the continental US is in Alabama, and it's got Dresser Rand equipment on it. And for those who maybe aren't familiar with K's, compressed air energy storage systems, basically you've got an air compressor, and when electricity is cheap or there's excess electricity on the grid, you run your air compressors, you compress air, pump it underground, usually into a pre-existing cavern of some kind. It could be a naturally occurring cavern. It could be one that used to have natural gas in it that's depleted. It could be a salt cavern where you actually dissolve water and make your cavern. But it's basically a big pressure vessel. So you store energy in the form of compressed air underground when power is cheap. And when you want to make power, you expand it out through a turbine and make electricity. So that system was installed in the 90s, I believe. Obviously, with the real big increase in renewable energy, primarily in solar and wind in the last 5-10 years, there's a lot more interest in energy storage technologies, whether you're talking about batteries, whether you're talking about making hydrogen via electrolysis, which is something else Siemens is involved in, whether you're talking about compressed air energy storage. Pumped heat is another thing where we're looking at that as an energy storage technology. So we're working with a few different customers, both in the US and globally, on kind of next generation compressed air energy storage plants. There's actually one in Utah that we're, these are big projects, many hundreds of millions of dollars. So it takes a long time to do anything. But the premise there is that wind turbines in Wyoming will charge caverns in Utah, which will then be able to make power to deliver to LA when they need it. So that's one project we're involved in at the moment that we're hoping to see actually turn into reality.
Do you know what the efficiencies of that are? I got a pump water is pretty high.
Yeah, pump hydro, right, is something else that's been around a while. Now the efficiency is pretty low. They measured in the 20s. So it really comes down to, that there are some times that have occurred in California, in Germany, where power prices have gone negative. There's more power, you've got to shut resources down. So in that kind of scenario, that's where, low efficiencies can pay off, or be a money-making proposition. And in terms of scalability, compressed air energy storage is one of the few that you can really scale with big kind of utilities scale numbers. You know, as opposed to, you know, batteries, which are certainly getting better, but you know, it's tougher. There's a lot more cost penalty to scale a battery up to hundreds of megawatts than it is to, I bought an air compressor to run it for longer, right? Just get a bigger cavern, right? So those are, you know, what we're involved in.
Thanks.
Yeah.
What do you think the biggest challenge for the oscillating water column is, like, from here? What's stopping it? What's stopping it becoming?
It's the levelized cost of electricity. When you build a 900-ton barge, effectively, the good news is it's pretty simple as a box. And the turbines, relatively speaking, pretty simple. But when you look at how much power you're going to get out of that versus what it costs to make that, what it costs to put it offshore, run an undersea cable, right? Onshore, there's just a lot of cost there. You pencil out the numbers, you're going to say this does not make sense. And trust me, I hear that from my bosses all the time. Because as part of an R&D organization in a gas and power company like Siemens, there's a lot of other guys competing for development dollars too. And if they can say, hey, here's a product we can roll out in 2 years and it'll be a moneymaker, and you got to say, well, in 10 years, right, maybe we'll be there and maybe we'll actually sell something. So that's just another reality of, you know, some of the work we do, trying to get the money to even do it. But we've got to drive the costs down is what it comes down to. Now, to me, one of the marrying offshore wind turbines, which are economically viable, right? Marrying this technology to that, because where you have high winds offshore, you've got waves. And where you've got offshore wind turbines, you already put the undersea cable in, right? And actually waves, right, they can be more predictable and more regular than the wind. So in terms of combining those two and helping smooth the overall power generation and leverage those other things you already have in place, I think that's the direction you got to go. In the near term, I think our best bet to actually deploy the technology is actually the Navy, because I think there's some smaller scale, and they're going to have some pretty niche applications that, you know, Puget Sound Energy is going to have, right? And they're going to want to recharge an unmanned underwater vehicle in the middle of the Pacific on some remote platform that's making its own power. Okay, and they're willing to pay for it, right? So I think in terms of getting real commercial deployments and sales, it'll be those kind of niche markets will have the most luck at first.
All right,
Here's
second
Bill.
speaker ahead of time.